You mean inside this, inside here? Yes, you can say E is less than B, same thing. Okay. And we have one more thing to take care of. We don't know what kind of a loop this is, the way it is right now. Should it be a pre-checking loop or a post-checking loop? This one is actually somewhat obvious. It has to be a post-checking loop. It has to be a post-checking loop because if I turn this into a pre-checking loop, M does not have a useful value yet. Because the condition involves M. If I turn this into a pre-checking loop, at this point, M does not have a useful value yet. So that's why this has to be a post-checking loop. Okay. Knowing this is a post-checking loop means I just have to turn begin loop into a repeat and end loop exit when into until. And we can combine these two lines back into one, kind of like that. All right, one more thing to take care of, because certain things have to be initialized. Let's take a look at the variables that we have here. Does K have to be initialized explicitly in this algorithm? Does the algorithm know what value we should be looking for? No, it has to be given, but it cannot be initialized in the algorithm itself. What about M? Should we initialize M before getting into the loop?
You can't, because you don't know what's all in the array.
Exactly. Plus, it's going to be overwritten anyway. The first thing in the loop, it will be overwritten. Right. What about B and E? They should be initialized. Yeah. Do we know how to initialize B and E regardless of what we are looking for?
E equals 0 and E equals the index minus 1.
Yep. Size minus 1. Number of elements minus 1. So B represents the beginning of the entire array, which means the index of the beginning of the entire array is 0. E represents the index of the very last element of the array, which is bar A bar minus 1.
First, you don't need to do bar A bar 0? Or, A bracket 0?
Nope. No, A bracket 0 is one of the values in one of the elements in the array, and I don't need to initialize that. That's given to me.
Oh, okay.
Yeah. The individual values of the elements have to be given to me, as well as the key. What I'm looking for also has to be given to me, because I don't want a search algorithm to only look for a particular value. I want that value to be specifiable by whoever is asking me to do the search. Very good. So here is a question that you guys can probably answer almost right away. If I forget the plus 1 here and I forget the minus 1 here,
Keep doing the same numbers over and over.
well, it won't keep the same. Eventually, yes, but initially they will still move because because every time you're still dividing by half. Okay, but at some point they won't move anymore, and we are guaranteed that if K is not in the array, this will be an infinite loop. Right?
Yeah.
Without the plus 1, without the B plus 1 or the E minus 1, they can never cross over. Just by dividing something, they can approach, they can be the same thing, but they can never cross over. And therefore, the loop will never exit without the B plus 1, the plus 1 part, or the minus 1 part of M minus 1.
So we basically creating an example of Casino's paradox, where if you go halfway some way, you'll never get there.
Mm-hmm.
Try crossing a bridge halfway, then you turn around and go back halfway.
Kind
go
of.
halfway across the bridge, you can go halfway across the bridge, and halfway is remaining.
Mm-hmm.
You only go
Right.
halfway every time, you never reach the other end.
Right. Yeah, it's kind of like that, except in this case, you're moving both ends, but they never meet.
So you fall off the bridge in the middle.
You have to wait until the bridge gets blown by the wind and sways. Or you can wait for the bridge to contract because of temperature change, because then the half is no longer the same half that you were talking about earlier. Okay, so that's the algorithm. We can trace it a little bit, but instead of tracing it, because I know you guys can trace algorithms at this point, and this one does not have anything particularly tricky. Yep.
Aren't we
Yep. We use the floor function. It's the floor function returns the largest integer that is less than or equal to the number that are in parentheses. Let me say that again.
Yes.
So it just returns the integer, the number that's in parentheses.
For positive numbers, yes.
Right.
But not for negative numbers. Okay. Floor is basic. If the number is guaranteed to be non-negative, floor is the same as taking the integer portion of the number. Okay. If you're dealing with negative numbers, that is a different thing because negative. The floor of negative 2.1 is negative 3.
Right.
Because negative 3 is the largest integer that is still less than or equal to negative 2.1. Okay. So for whatever we are doing here, taking the floor function is fine, taking the integer portion of that number is fine, taking the ceiling of that function is fine, taking the round version of that number is fine. In other words, you can use rounding. If the number is more than 0.5, you round up. If the fractional part is less than 0.5, you round down. That works fine too. It doesn't really matter because when you have two middle elements, you can pick either one, and the algorithm will still work. Okay. Any questions at this point about the algorithm itself? Now, instead of spending the rest of the class, 15 minutes or so, tracing the algorithm, which is not really going to be very beneficial at this point because we kind of know how to trace algorithms already, and we have some examples already here. The only difference is instead of marking using the lines, we are moving B and E accordingly. Okay, so it's not going to be very exciting. What I want to talk about is the efficiency of a search algorithm. How do we assess? How do we quantify the efficiency of a search algorithm? Okay. Yep.
The least number of steps required to acquire a result.
The number of lines of code.
Now, in terms of number of line of code, this is longer than linear search. Okay.
But it's more
So the
efficient.
question is the linear search algorithm better, or is this algorithm better?
This one's more universal.
Okay, now here, let me give you a scenario first, and then we'll examine that scenario, and then determine, how do we exactly qualify, whether a algorithm is better than another algorithm. So let's say, Peter and I, work for the same, software company. The software company is downsizing, offshoring, and doing all that sort of stuff, so they don't need as many people in the United States anymore. And we're getting down to the point where either I stay or Peter stays. So the boss says, well, I don't want to, do everything by, I like Peter better and therefore Peter stays. I want you guys to compete, okay? I want you guys both to write a search algorithm. Whichever search algorithm is faster, I keep the person, who write that algorithm. Okay? Do you guys understand the competition, the nature of the competition? And then my boss says, well, since this is not cisp300, I will time you, I will clock you the actual time that the computer needs to search for a particular element in an array. So this is not going to be in pseudocode. We're not going to look at traces anymore. It will just be based on a stopwatch and actual code executed on a computer. Unfortunately, because I'm an old timer of that company, I have been using my 386 computer, for software development. And it's not only a 386; it's a 386SX, running at a whopping 16 megahertz. That's my computer. Lazy. And that's all I need to do coding, really. I mean, because I can telnet and SSH into a server and do development that way. I don't need my computer to be super duper fast. My colleague, Peter, on the other hand, joined the company last year. So he had the latest and greatest Core i7 with a quad core thing. Okay, 3-point-something gigahertz, 6 gig of RAM and all that good stuff. Okay? So now my boss says, well, Tech, I can't really give you the same computer just for this particular assessment to see who gets to stay in the company because we don't have a spare computer, right? So Tech, you'll be running your algorithm on the good old 386SX, and Peter, you'll be running it on your i7 system. And Peter is snickering and go like, Tech, you're going to be a goner, man. I'm going to smoke you regardless of what I do, right? Do you guys agree?
No.
In terms of, efficiency, in terms of processing power, the i7 of today, okay, when did the 386SX first came out?
84.
Approximately what year?
85, 86.
No, I think it's after 85. It's probably closer to 87-ish, 87, 88-ish. So about 12 years, okay? Is it 12? 12? No. No, that's like 22 years.
20, yeah.
So we're talking about 22 years. How many 18 months do we have in 22 years? Let's say 24 is easier, right? 24 divided by 1.5 is, gosh, I can't do arithmetic. 16? Okay. So we're talking about 16 18-month periods. According to Moore's law, you double the processing power every 18 months. So Peter's computer with an i7 core is supposed to be 65,536 times the speed of my good old 386SX computer. Okay, that's a huge difference in terms of processing speed. Okay, so we'll keep this in mind. And now we'll use a spreadsheet to do the calculations. Now, because Peter was so convinced that he will win the competition, he just picked up the first search algorithm that he could find online, which is the linear search algorithm. And he will say, regardless of what I do, I'm going to smoke Tech and I will keep my job, and Tech is a goner. So now we keep track of a few things. We want to first of all, keep track of bar A bar, how many elements in the array we are talking about. And then we'll talk about Tech's algorithm. Basically how many times my algorithm has to go through the loop, how many iterations that I have to go through to confirm an element is not in the array. And we'll keep track of Tech's computer's time. Okay, how much time will I need to go through that many iterations? We'll keep track of the number of iterations Peter's algorithm needs to go through, and also how much time Peter's computer needs to execute that many iterations. Okay, so now we have 5 columns. 2 of these columns are really the same thing. 2 of these are exactly the same thing, except one is scaled and the other one is not. When the array only has one element, I need exactly one comparison to confirm that that one single element is not the one that I want. Okay, I need one comparison. Peter's algorithm also needs exactly one iteration because to confirm that it is not the one that we need, he still needs to compare once. Let's just call my computer time, the unit time. So Peter's time is going to be, a small fraction of my time. We'll call the scale. Let's see. Okay, this is going to be this number times, my time divided by 65535 or 36, right? And why is it complaining? D1 divided by that.
Should be D2.
Oh, okay, right. Sorry. Okay, that's a pretty tiny number. Which is fine. Peter looks at that number and say, yeah, I'm winning. Tech, you are going down. You're going down. Okay, well, let's double the number. Okay, my algorithm, let's not double. Let's go to 3. Okay, the reason why we go to 3 is it's easier to analyze. With 3 items, the first comparison will compare to this one, eliminate either this half or the other half. Then the second part will only have one element left. So I need exactly 2 comparisons to handle 3 elements in the array. And since this is just really unit time,